Now the next we are having the imperfection in the solid. Imperfection, that is a fault in solid. Now when we are talking about the fault in solid, that is a defects in solid, then we know that in a crystalline solid all the constituent particles are present or they are arranged in a definite order. There is a fixed arrangement of a particle in a crystalline solid. But it has been, and if the particles are arranged in a definite order in a given solid, then such solids or such crystals are called as an ideal crystal. But it has been observed that the definite arrangement of the particle in a given solid is present only at a very low temperature, that is a absolute 0 Kelvin temperature. If the temperature is a 0 Kelvin, then only I can say that the defects, all the constituent particles are going to be arranged in a proper manner, that is a definite manner. As the temperature increases above 0 Kelvin, as the temperature goes on increasing, I can say that that fault goes on increasing. The defects in a solid goes on increasing. Now what defects we observe? Here we are talking about the defects with respect to the arrangement of the particle, or with respect to the arrangement of the particle. The arrangement get disturbed for the as the temperature goes on increasing. And here we are talking about all the solids generally at room temperature, the room temperature which is considered as approximately 298 Kelvin. So as I said, the solid is going to be defectless, or there will be no imperfection only at, it will be a perfect only at 0 Kelvin temperature. As the temperature increases, the defects arises or it goes on increasing. So the solid which we are observing at 298 Kelvin or 300 Kelvin temperature, that is approximately room temperature, is going to have a large number of defects. So here we are going to learn about those defects which are generally observed in a case of solid. Now what defects we have? So there are actually two types of defect. The one is called as a point defect. The point defect, I can say it is a defect or it is a fault with respect to the arrangement of the constituent particle, that with respect to the lattice point. But this is the defect which do not affect the surrounding particle. This is defect which is associated with a given lattice point, does not affect the surrounding spheres or position, or it does not create any problem to that surrounding particles. The second which we have is called as line defect. Now what is line defect? The line defect, that is when the fault or irregularities in arrangement is occurs throughout a line, then it is called as a line defect. Means when all the particle along a single line is arranged in an irregular manner, then it is called as line defect. So we have two different types of a defect, that is one is called as a point defect and the second is called as a line defect. Here in a syllabus we are having only about the point defect. So here we are going to learn about the point defect. Point defect, it is again of three types. The first one is called as a defects, the stoichiometric defect, non-stoichiometric defect and the impurity defect. So let's start with the first one, that is a stoichiometric defects. So the first one, the point defect. Point defect in stoichiometric compounds. Defects in stoichiometric compound. In stoichiometric compound, we are having generally two types of defect. The one is called as vacancy defect and the second one is called as interstitial defect. So here in this part we are that is the first type we are going to learn about these two defects, that is impurity defect and vacancy defect and interstitial defect. When the same defect is observed in an ionic solid, then we have one more name for it, that is called as Schottky defect. And when the interstitial defect is observed in ionic solid, then we have one more name for it, that is called as a Frankel defect. The names are given on the basis of its discoverer, that is a Schottky and Frankel. So let's start with the vacancy defect, that is what happens in the case of vacancy defect. So the first type which we have is vacancy defect. What happens in case of vacancy defect? I can say that in case of vacancy defect, the constituent particles are missing from their position. The particles at the lattice point, the particles are not there. The particles are absent. That means we say that they are missing from their position. So vacancy defect or vacancy. So, and as I said, when the same defect is observed, for example, suppose if it is a molecular solid, then from certain molecules will be missing from their position. If it is a covalent solid, then certain atoms will be missing. Means the certain atoms are missing from their position. And when the same defects is present in a ionic solid, then we have, as I said, we have one more name that is called as Schottky defect. So vacancy defect and Schottky defect is nothing but the same, but the Schottky defect word is used only when the solid is ionic solid. In other cases, only the vacancy defect the name is used. So let's talk about this Schottky defect now. What happens here? Okay, now in this case, I'm considering an ionic solid. The ionic solid which is made up of cations and anions, and those cations and anions are arranged in a alternately, that is, after every cation there is an anion, after every anion there is a cation, and we are talking about the stoichiometric. That means after the defects also, after imperfection also, the number of cation and the number of anions should be in the stoichiometric proportion. So let it is plus minus, that is cation, anion, then again cation, again anion, again cation. So let I have this ionic solid. This ionic solid, which example I'm saying that it is an NaCl solid. NaCl solid, that means these are the Na plus and Cl minus, Na plus and Cl minus n. As I said here, the constituent particles are missing from their places. The constituent particles, in this case, now here you can say currently it is representing an ideal crystal because all the particles are present and all of them are arranged in a definite order. That means, as I said, after every cation there is an anion, so you can see the same arrangement. That means here currently there is no defects in a particular solid. Now, what is vacancy defect? Vacancy defect as I said, particles are missing. Now, in case of ionic solid, what is particle? In case of ionic solid, the particle, once I use a particle, means it is going to be a cation and anions. So here the cations and anions are missing from their places, leaving the vacancies behind. That means once they are absent from their actual position, no other particle comes to occupy that position. So cation and anions are missing. So suppose this cation is present here, I am saying that this cation is missing from here, this point. Similarly, let there is a no anion, I can say that anion is missing from here. So I can say, here you can see that cation is missing and from here anion is missing. So ultimately, this is called as vacancy defect. So there is a no cation, there is a no anion. So these are nothing but the vacancies which has been generated due to the absence of the cation and anions. And so here I can say that cations, constituent particles are missing. Now see, once I am saying that constituent particles are missing, it means what? It's not like there was initially a particle and then move away. The thing is, if I am saying constant particle is missing, it means during the crystallization process, means when suppose when the solid was getting converted into a liquid, was getting converted into a solid, then that conversion was too fast. When defects is generally observed, see, when crystallization is very slow process, the defects are very less. But if the rate of crystallization is very fast, then defects are very large. Now crystallization means what? The conversion of a liquid into the solid state. Now what happens in the case of this? Suppose the crystallization process was little bit faster, and when the crystallization process is fast, then these particles which are present, that is a cation and anions, they do not get enough time to arrange them in a proper manner. So since the cation and anion do not get the proper time to arrange themselves, and that's why we get a fault, that is an imperfection in solid. So what happens in the case of this, during the crystallization, the cation and anion didn't get the proper time to arrive there, and since the cation and anions didn't reach here, so we say that the particles are missing from their places. As the rate of, if the crystallization process is very fast, this arrangement are like goes on in this imperfection goes on increasing, because the particle didn't get the proper time for it. So constant particles are missing. Here the constant particles are nothing but the cation and anion if it is a Schottky defect. Now this is observed generally in those ionic solid which have a higher coordination number. So it is observed in those ionic solid which have higher coordination number. Now higher coordination numbers are present in those ionic solid where the cations are bigger in size, because if the cations are bigger in size, then they occupy bigger void, and if they are occupying bigger void, that means their coordination number is going to be large. So here I can say this is observed in those ionic solid where the cations and anions have approx same size. Approx same size. Okay, after this, so as I said here, the cation and anions have approximately same size. Now in the case of vacancy defect, as the vacancy defect goes on increasing, here the density of the solid, what happens to the density? The density get affected. Now let's see what happens to the density. The density, the formula is mass upon volume. The mass is because of these particle upon the volume, that is total occupied area. So here the mass is, I can say that if the defect, when the defect increases, the particles are missing, that means the mass goes on decreasing. And what about the volume? See here, once the particle is missing from here, the particle is not there, that means but no other particle is, means that area remains vacant, that is the volume does not changes. So here I can say the mass decreases and the volume remains constant, and if the mass is decreasing, that means the density will also decrease. So this vacancy defect produces a decrease in density. So it decreases the density of the solid, that is a Schottky defect. And example, it happen or it occurs generally in the case of those ionic solid where the cations and anions have approximately same size, because here the requirement is the higher coordination number, which is possible only when the cations are larger in size, like NaCl, NaBr, CSCl, etc. Now in case of vacancy defect, I can say here when the cations and anions are missing, they are absent in a stoichiometric proportion only to maintain the neutrality of the solid, so that the solid should remain neutral. And since here the particles are missing in their stoichiometric proportion, that's why it comes under the stoichiometric, means this is called as a stoichiometric defects. That is a first type of the point defect. Now after the vacancy defect, we have the next type of the stoichiometric vacancy point defect is interstitial defect. Now let's see the second one. Interstitial defect. Now what happens in this case? This is generally observed in case of ionic solid, and when it is observed in case of ionic solid, we call it as a Frankel defect. This is another name for it. In short, I can say. So we have Frankel defect. Now what is Frankel defect or interstitial defect? It is a defect in which the cations, this is generally observed in those ionic solid where the cations are very much smaller than anions. And since the cations are very much smaller than anions, that's why the cations migrate from its actual lattice point to the interstitial points. Cation being a very small in size, they migrate from its actual lattice point to the interstitial lattice, interstitial spaces. Now interstitial spaces means the spaces which are left between the particles. For example, suppose if I have this ionic solid AgCl, cations are very small. So as I said here, the cations being a very small, it migrate from actual lattice point to interstitial. These are the interstitial points which are left between the particles. Means I can say interstitial is nothing but like a void only, another name of a void I can say. So and the cations are already present in a void, so it is it migrate from actual lattice point to some interstitial places, means some anywhere where the spaces are left between the particles. So suppose in this case, this particle here, the cation was present. Now let this cation is migrating from here to let this it migrate to this point. So the actual lattice point of this cation was this one, but now it has been migrated to this point. So this is called as interstitial defect or the Frankel defect. Okay, so this is the interstitial cation which is present here. Now so as I said here, the constituent particle, especially cations, but in some cases it may be anions also. Depending on, I can say, the one which is smaller in size migrate and the one which is bigger in size remains as it is, means it doesn't migrate. So here the cations, being generally in majority of the ionic solid, the cations are smaller in size and hence the cation migrates. So cation migrate from actual lattice point to interstitial site. This is observed in which the cation is a smaller in size, and if the cation is a smaller in size, then it will occupy a small size void, and if it is occupying a small size void, that means it will have a lower coordination number. So this is observed in those ionic solid which have a lower coordination number. Then next, here as I said, the cations are smaller in size. And this, how it affect the density, let's see whether it will affect density or not. Again, the density, the formula is mass upon volume. Here I can say that the mass remains approximately same, because here the particles are not missing from their places. It's just migrating. That means the number of particles remains same and the volume occupied also remains constant. That means neither mass is changing nor the volume, and hence the density will remain unchanged or it will remain constant. So does not affect density of the solid. So it does not affect density of the solid. And then example which is it is observed in the solid, like I can say AgCl, AgBr, AgI, zinc sulfide, etc. Because these all are the solid in which the cations, like in case of AgCl, I can say the cation Ag is very smaller than anion. Similarly in ZnS, I can say zinc ion is smaller than sulfide ion. So this defect is observed. So and now let's see what happens, what difference is observed due to this defect. Now in the case of this, since the cation and anions are missing from their places, ionic solids are in a solid state. The ionic solids are generally considered as a bad conductor of electricity, because in solid state these ions are not free to migrate. Now but what happens here, once a cation is missing, once one ion is missing from here, then on supplying electricity, suppose I just wanted to know whether after increasing electricity, whether the defects, after supplying after the defects, whether the electrical conductivity has changed or not. So when the electricity is supplied, this vacant space is occupied by this cation. If this cation comes to here, that means here a hole will be created. Then this space will be occupied by this cation. This space will be, means what happens here, this holes keeps on changing. From this here, holes migrate to this, then holes migrate to this, then holes migrate to this, because every cations or every anion just occupy the vacant space. So the new vacant space or the new hole is created. And since there is a movement of the holes, and that's why here I can say in a Schottky defect, the electrical conductivity increases on increasing a defect. In case of Frankel defect, the same thing happen. A hole is created. So when electricity is supplied, this cation comes to this, so that hole is created here. This cation comes to this, so the hole is created here. That means again here I can say the hole is moving or the ions are moving, and since the ions are moving, that's why again the electrical conductivity has been increased. As I said, as the temperature increases, the defects goes on increasing. At a room temperature, it has been observed that there is a 10⁶ Schottky defect present in case of NaCl. In case of NaCl, there is a 10⁶ Schottky defects is observed per centimeter cube area in a NaCl. In a 1 centimeter cube, 10⁶ places are missing. That means 10⁶ places are vacant. And in 1 centimeter cube space, how many lattice point is there? 10⁻22. That means if I'm taking a NaCl at a room temperature, then it have 10⁻22 particles, out of which 10⁶ particles are missing from their places because of this Schottky defect. If you are increasing a temperature, this 10⁶ value will again goes on increasing. From 10⁶, 10�7, 10⁸ particles will get missing. Now in case of Frankel defect, only, here I can say that the charges comes more closer. Due to this, when the constant particle or the cation migrate to the interstitial spaces, the charges comes more closer, and since the charges comes more closer, so the dielectric constant of the solid increases. Dielectric constant, which measure the permittivity of a substance, so it goes on increasing. Such thing doesn't happen in case of Schottky defect, because here the charges doesn't comes closer. So this happens only in case of Frankel defect. So as the Frankel defect increases, the charges comes closer, and due to which the dielectric constant of a solid goes on increasing. So we are having these two types of the defects: point defect, that is a vacancy defect, and interstitial defect. For ionic solid, we are having two more. The names are the Schottky and Frankel defect.